Hey everyone, this is Michael Buckley at Side Effects, and today I'm going to be showing you how to do uh, interesting technique for varying geometry in SOPs using tops um, via the invoke top and compile blocks. So basically, it's an alternative to traditional for loops in Houdini. Allows you to um, vary parameters in instead of in a loop, uh, do it in parallel using the aforementioned invoke top. So let's dive in. Okay, so here we are in a geometry network, and I've got this guy here. I'm calling it a pedal. What we're going to be going for is something like this, where we take this guy and we kind of rotate him and twist him a little bit, and we do that a number of times, and then we'll put it through a vellum simulation, and the result will be something like this, where you have this kind of like abstract kelp like form. So that's kind of the plan. That's what we'll be going for. To do that, we've got to duplicate this guy, twist him, and also going on here is a little bit of length variation as well. So uh, how would we do that? Well, we have a twist SOP, and if I go into the viewport state for this, I can make sure it's aligned correctly by hitting the B key. Okay, great. And this will handle the twisting. So good, we got that. And this will also handle the, if I turn on length scale, it'll also handle the stretching and foreshortening. We want to have a little bit of variation there as well. Okay, great. Let's get rid of that. We'll talk about the other aspect, which is going to be a rotation. So for that, we can achieve that with a transform. And so basically just simple rotation. It's already this point is already at the origin, so the pivot already works for us. Okay, great. So then now we basically just need to do this bunch of times. We got to order the twist first, and then merge everything together. And I think the tool that most Houdini users would reach for in this case would be a for loop, and that's certainly a viable option. But today I'm going to show you another way that you can achieve the same effect. So let's pull these guys out and let's wrap them up inside a compile block. Okay, and put them inside. And note that to be compilable, you have to use you have to look for the nodes that don't have a gear flag on them. That would mean they're not compilable. Make sure you have that flag active. So I do. You might have it to set to hidden, in which case all your nodes will not have this flag. So make sure the flag is there, and you can see which nodes actually are compilable. That's one limitation of this technique. But for nodes that are compilable, put them inside the compile block. And now let's put down a top geometry node, and let's plug our input into the top geometry. Okay, and right now this is actually set to read in. The way this works is basically tops, for the most part, works with geometry off disk. Most top nodes that actually do work will take geometry off disk as inputs, but the invoke top actually has the ability to work on in-memory geometry. So we can avoid disk writes by using that feature. And we can also then directly import that in-memory geometry after TOPS is done with it right into SOPs again. So we never have to write anything to disk. So let's do that. Let's set the output to geometry attribute. Okay, now it's complaining that there's no geometry attribute named geometry on the work item. So let's dive in and see what that's about. And we'll see that we get for free this kind of geometry import included that is set to pull in geometry from the node that we have wired in to the top geometry SOP, which is great. That's what we want. But we currently have it set to store the geometry as an external file. So we actually don't want that. We want to keep everything as geometry. So we're just going to set that to the geometry attribute. And now if we actually middle mouse button on the work item, we see it has this thing, which here, this is a geometry attribute. This is an actual piece of in-memory geometry that we'll be working with on all further work. And we can see that it's actually drawing in the viewport. So that's great. So all we have here basically is we're passing this thing in, we're creating one work item, and we're doing nothing, and then we're pulling it back out. But what we really want to do is we actually want to pass some that work item into this compile block and perform whatever is going on in this compile block on it. One thing to note, in addition to basically being able to, take the network inside a compile block and pass in-memory geometry through TOPS and distribute that work in parallel, which is useful. The compile block also compiles everything inside of it, which is nice. You can potentially get performance wins just by having the network inside a compile block. That it allows basically the network inside to be optimized as well. So it's potentially going to actually run even faster than if it was just outside of the compile block. Let's get going. So let's put down an invoke node. So the invoke node will take any work items that it generates and run them through a compile block. We have to give it a compile block to work with. So we'll come back up. I'm going to just Control C to copy the end node and come back in here and just paste it in there. Okay, now we've got some parameters got activated for us. So we have an input count parameter, and we have a write geometry to, and we're going to write to attribute, so that's fine. This input count, we definitely want to input our geometry into the compile block, so we need to add +1 there. Our geometry source is going to be upstream geometry data, and its name is geometry, so that works for us. Now we need to give it a name. So I'm going to say its name is in. I come back here, and to my begin node, I'm going to place in there as well. And the reason that we have to specify a name is because you could have multiple input nodes for the network inside the compile block. So this is just specifying, like, if you have multiple upstream work items, which geometry actually goes into what compile block begin node. Okay, so that looks good. So let's see what happens. Okay, we got the node in here. Let's see what happens if we cook. It cooks successfully, and just sure. Okay, great. And it's doing what's in that network, which is great. But we want to do it more than just once. So let's do this. Let's put a wedge node in there, and all we're going to do on the wedge node is just increase the work item count, just to verify that this is going to do the right thing. And you see, as we increase that wedge count, it actually immediately goes ahead and cooks that stuff. And if I look at, let's see, primitive count, I wonder what will actually give me a good idea. This is all going to be geometry that's sitting on top of itself. Do we actually, yeah, it looks like we do actually have, let me actually do one of these. Double click it, hit T. I just want to verify. Okay, yeah, we do in fact have multiple now. We actually now have, was it 10? Yeah, we now have 10. This compile block is being run 10 times for each work item that we see in here. Okay, cool. Now, this is the interesting part. So we don't want to just do the exact same network 10 times. We want to vary the twist, and we want to vary the rotation. And we can actually do that. We actually control those two things by work item attributes. So I'm going to actually, coming back to my wedge node, 10 is fine. I'm going to add some attributes now that we're going to want to wedge. Okay, so the first one we'll call twist. It's a float, and the twist takes degrees as its unit, so we want the range to be around 360. Let's say 720 to 360. We want to twist at least once around, and we can actually set that to random. And then we also want a length. Oh, let's do this. Let's do the rotation first. We want a rotate value as well. And this is also going to be specified in degrees. This is going to go up to 360. Okay, and we don't want this to be random. We actually want this to be kind of evenly distributed across the work items, which is what we'll get if we don't check on random. And now we can actually look and see what those values are. Okay, so we have rotate, 0, 40, 80, that looks good. And we have some random twist values in there as well. Cool. Okay, that's what we want, but obviously we're not seeing any difference because we haven't applied those values to this network. So that's what we'll do right now. So typically when you use top attributes to drive a network, you can express them like this, where you have an @ sign and then the name of the attribute after the @ sign, and then that will get automatically populated. That won't work with this technique. You have to actually use to get to work inside a compile block, and this comes from the fact that these are compiled basically like this. Effectively, we're working with almost like a single operator in effect when it runs, that this all gets compiled. So everything we need to possibly give it needs to know about ahead of time. So for that reason, for some reason, we need to use P2G attrib. We can't use the @ sign to wedge this network with top attributes. So that's actually, it's not too bad. You basically just need this little HScript function called P2G attrib, and you just do open quote, type twist, close quote, and then takes an integer to specify possible component, because that attribute could be a vector, it could be an array. It's not in this case, so let's put 0. Okay, so now we've got the twist specified, and I'm actually just going to, I put backticks around it out of habit because I work with strings a lot, but that's actually not a string, so that should not need backticks. Okay, so I'll copy that and actually just paste this right into, I'm actually going to paste this now into the rotate value, just so we don't have to type everything out again. And I'm going to type rotation or rotate. Okay. Cool. All right, what do we got here? Does that look correct to us? So we got 2 intersecting here. So that's actually good because we can see that these are intersecting. And the reason they're intersecting is because the way that wedge top works is it will actually create, when we don't vary the attribute values randomly, it'll kind of do fence posting, where it'll put like, okay, so what the first work item will have a 0 rotation, and the last work item will have 360. So both ends of the range get a work item. So that's actually useful because we can now see that our twist is in fact working, because it's somewhat slight. We might want to crank that up a bit, but that's good. So yeah, so now we've got that working. If we come in here and let's actually just do something to get rid of that. So I'm going to do filter by range. I'm going to put that in here. Keep items in filter range, not frame, but index. Index 0 to 0. We're just going to take out that first work item. I'm going to remove that. Okay, that gets rid of that. But now we can vary those values in here, and we can also vary the number of iterations we're doing. And you can see this is super fast, because not only is it running a compiled network, but it's also doing it in parallel. So that's performance-wise, it's excellent, and we can vary the values now. Like, let's take this up to 2,000 and see what that gives us. Okay, it's kind of interesting. You take this down maybe to 50 and have some ones that don't really vary a whole lot. Just have a bigger spread there. And let's also create another, just to add some interest to it, we're going to create another attribute and call it length. And this is going to be a range from, let's say, 0.5 to 1.5. Do random samples as well for it. We're going to come back up to the twist and enable length scale. And we're just going to put that that length scaling out too, just to give it a little bit more of a variation. 0. Okay, I think I'm gonna have to recook to see it. Ooh, now we've got some really short ones. Okay, let's come back in here. 0.5 might be too extreme. Okay, 1.1. Oop. Okay, let's come back up here. Capture length, capture direction, capture origin. That could be off. Let me just come back over here and vary this and just make sure that we're dealing with the right thing. We basically need a length that will work for every single one of them. And I think that might be throwing this off. So we want the origin to be actually there. We want the direction to be along X. And the length should be fine. Yeah, so 10. And then we're scaling it effectively to 0. Let's just turn these off so I can see them without any overrides. Okay. Okay, so I think a length scale of 10, that will work for all of them. Trouble is this was set already. We kind of moved this over after we plugged the manual setup into it. So I'm actually going to set this to values that we know will work for everyone, and 11 is going to be fine, I think. Okay. Okay, that gives us a much better result. So now we've just got a little bit of variation of the length around here. Cool. And then just to kind of cap it off, we'll put this through a vellum figure cloth and do a vellum sim vellum solver. All default settings, doesn't matter. Simulation, forces, going to turn off gravity, going to turn on wind. I'm just going to show you how I was able to generate that image we saw earlier. And then play it forward. Oh, we also want to turn off self collisions as well. We don't want this to collide with itself. And now if we come forward, we're going to see a little bit of action here. It's going to kind of twist and need to resolve itself a bit. Cool. I think I actually set the wind force not in Z, not in Y, but in Z. Let's look at it now. Cool. So that's the tutorial. That's how you can use tops to wedge compile blocks. Hope that was useful. Thanks for watching.